A single query on an AI platform like ChatGPT consumes, on average, 10 times more power than a simple Google search. That might not sound like much, but it's the tremor that precedes a tectonic shift in our world. Because the infrastructure behind that query isn't just a server, it's an entirely new kind of factory, an AI factory. And these factories, now springing up across the globe, are on the verge of consuming as much electricity as entire countries. This isn't just a story about technology getting more powerful, it's about what that power actually consumes. Raw, brute force electricity. The explosive, insatiable energy demand of artificial intelligence is creating a silent crisis. It's a crisis that will stress power grids to their breaking point, rewrite our economy, and forge a new world order. The question of the 21st century is no longer just who has the best data or the smartest algorithms. It's now much more fundamental. Who has the power? The answer will determine which nations rise and which fall. To get a handle on this crisis, we have to look at the machine that's causing it. When you hear factory, you imagine smokestacks and assembly lines. An AI factory is different. It's housed in a data center, a vast, nondescript building that could be anywhere. But make no mistake, what's happening inside is a new form of industrial production, on a scale the world has never seen. For decades, computing has been about efficiency. A Google search is a masterpiece of that. A fuel-efficient sedan designed to find information using the least energy possible. An AI query is fundamentally different. It's not a sedan, it's a fleet of 18-wheelers. It doesn't just retrieve information, it engages in a complex process of reasoning and generation, mobilizing vast computational resources to formulate an answer. The engines inside these AI factories are graphics processing units, or GPUs. These specialized chips are the workhorses of the AI revolution. One company, NVIDIA, has a staggering grip on this market, controlling roughly 80 to 90% of the GPUs used for AI. These chips are marvels of parallel processing, performing trillions of calculations at once. But this power comes at an enormous energy cost. They are power hungry, generating immense heat that in turn requires even more energy for cooling. These aren't your desktop graphics cards. They are industrial-grade engines running at full throttle 24/7. Their work is split into two phases, training and inference. Training is the phase you've likely heard about. It's the process of building an AI model by feeding it colossal amounts of data, texts, images, code, and having it learn the patterns within. This process is incomprehensibly energy intensive. For perspective, training a single major model like GPT-3 can consume as much electricity as about 100 US homes do in an entire year. For a long time, many assumed this was the main energy problem. They were wrong. The real enduring crisis comes from the second phase, inference. Inference is AI in action. It's every single time you ask ChatGPT a question, generate an image with Midjourney, or use an AI-powered feature. Each query requires a significant burst of power. While the numbers vary, a single inference query can consume around 10 times the energy of a standard Google search. Individually, it's a small number, but the scale is planetary. Billions of these queries are now happening every day. And unlike training, a periodic event, inference is a constant, relentless, and ever-growing hum. This is the quiet secret of the AI revolution. It's not the building of AI that will drain our power grids, but the daily, hourly, second-by-second use of it. The inference phase has overtaken training as the dominant consumer of electricity, and that has profound implications for our global energy infrastructure. The numbers behind AI's energy consumption are so large they are difficult to grasp. Let's start with a recent baseline. In 2024, data centers worldwide consumed an estimated 415 terawatt hours of electricity. That's already a massive figure, approaching the annual energy consumption of a country like the United Kingdom. Now, let's look at the future. The International Energy Agency, or IEA, projects that by 2030, in their base case scenario, data center electricity consumption will more than double to around 945 terawatt hours. That is roughly equivalent to the entire annual electricity demand of Japan. Imagine building a second Japan and plugging it into the global grid. That's the scale of what is happening. The IEA has identified AI as the single most important driver of this growth, projecting a blistering growth rate of about 15% every year through 2030. Some high-end projections warn that by the end of the decade, AI data centers could be a major driver of new electricity demand globally. While this is an upper-end forecast, the very fact that serious analysts consider it a plausible scenario reveals the magnitude of the challenge. This isn't a distant problem. It's happening now. In the United States, data centers already consume over 4% of the nation's total electricity. That figure is on a trajectory where AI-specific servers could significantly increase national energy demand by 2028. What's driving this growth? It's not just that more people are using AI. It's a classic economic principle, the Jevons paradox. The paradox states that as technology makes using a resource more efficient, our overall consumption of that resource often increases, not decreases. As AI models become more powerful, we discover exponentially more uses for them. They are being integrated into every industry and every service. And the models themselves are becoming more complex. While the GPUs running them are getting better, the size of AI models is growing at an even faster rate. The result is that any efficiency gains are being swallowed by a tidal wave of new demand. We have created a machine with an infinite appetite, and we are only now beginning to grapple with the consequences of trying to feed it. For most of us, electricity is magic. Flip a switch and the lights turn on. But behind that switch is a complex and aging system, the power grid. And that system is starting to buckle. The poster child for this crisis is a region in the United States called Data Center Alley. Located in Northern Virginia, it's the largest concentration of data centers in the world, handling a huge portion of global internet traffic. For years, it was a symbol of progress. Today, it's a warning. In recent years, the energy demand from these data centers, supercharged by the AI boom, grew so fast that the local utility, Dominion Energy, had to do the unthinkable. They announced a halt to new data center connections in parts of the region. The grid had literally run out of power. The problem has only escalated. As of early 2026, Dominion reported it was facing a queue of requests from data centers for a mind-boggling 70 gigawatts of power. For perspective, a large nuclear power plant might generate 1 or 2 gigawatts. This is a demand pipeline equivalent to dozens of nuclear power plants for one region of one state. The issue isn't just the amount of power, it's the way it's consumed. Grids are built for predictability, the rolling waves of demand as a city wakes up and sleeps. An AI data center is different. It's a constant high-load customer, pulling a massive amount of power 24/7. This creates a huge, unrelenting load on the system. This kind of load creates unique technical challenges. It can cause instabilities that can cascade through the grid, leading to brownouts or even widespread blackouts. The grid is being asked to do something it was never designed for. What happens when the hospital, your home, and your city have to compete on the same wires with the voracious appetite of AI factories? We are beginning to find out. Utilities are now scrambling to build new power plants and transmission lines at a pace not seen in generations, just to keep up. This infrastructure crisis has a direct impact on you in the form of your monthly electricity bill. The laws of supply and demand are unforgiving. When demand for something skyrockets and supply struggles to keep pace, the price goes up for everyone. The AI boom is creating unprecedented demand on grids that are already strained. Utilities have to respond by rushing to build new power plants, investing billions in upgrading old transmission lines, and planning massive, long-term generation projects. These costs are socialized, passed down to every customer on the grid, from a small business to a family home. In Virginia, residents are already facing rate hikes to help pay for grid upgrades driven by Data Center Alley. It is, in effect, a hidden tax for the AI revolution. You are paying for the energy that powers the cloud services and AI models that are reshaping the economy. The giant technology companies building these AI factories have become some of the largest energy consumers on the planet. They are now in direct competition with you for a finite resource, and that competition is driving up the price for everyone. This creates a deeply uncomfortable dynamic. As AI promises a future of abundance, its very operation is making a basic necessity, electricity, more expensive. The abstract benefits of AI are in the future, but the rising cost on your power bill is here and now. The promise of a digital utopia is being paid for, in part, by a surcharge on the real world. This brings us to the heart of the matter. This isn't just an infrastructure problem, it is a geopolitical event. For the last century, the world order was built on oil. Access to cheap fossil fuels determined industrial might and economic dominance. In the AI age, a new commodity is taking its place: cheap, abundant, and reliable electricity. The race to lead the 21st century is fundamentally an energy race. Right now, only a handful of organizations can afford to play at the highest levels of AI. Companies like Google, Microsoft, and Amazon are spending billions not just on researchers, but on the colossal infrastructure required to power their ambitions. The cost of energy is becoming a primary barrier to entry, creating a world of AI haves and have-nots. This dynamic isn't just happening between companies, it's happening between nations. The losers will be nations with expensive or unreliable energy. Take Germany, a longtime industrial powerhouse. It now has some of the highest electricity prices in the developed world, making it an unattractive location for the massive AI data centers that will power the next generation of industry. German companies may design the world's best machines, but if they have to rely on foreign-owned AI infrastructure, they risk becoming technologically dependent, slipping from being a leader to being a customer. The winners will be the nations with an energy surplus. This is the new definition of a resource-rich nation. Look at the countries positioning themselves to dominate. Norway and Canada have vast, cheap hydropower, but more strategic moves are happening elsewhere. For a century, the Middle East power came from oil. Now countries like Saudi Arabia are looking to the sun, aggressively investing in massive-scale solar power to achieve record low costs. This isn't just about climate goals, it's a calculated pivot. They understand that the world's cheapest electricity will attract the world's most important new industry. They are planning to turn a natural advantage in sunlight into a strategic advantage in artificial intelligence. Then there is China. Beijing has made its ambition to lead the world in AI by 2030 clear. They understand this requires a colossal amount of power and are executing an all-of-the-above energy strategy. Most notably, they are in the midst of a nuclear power building spree unlike anything the world has seen, with construction timelines far faster than in Western nations. Some reports suggest the U.S. is now 10 to 15 years behind China in deploying the next generation of high-tech nuclear reactors. This is a deliberate, state-directed policy designed to secure the one resource that will underpin their geopolitical ambitions. The new logic is simple. Access to cheap power is no longer just an economic advantage, it's a prerequisite for technological sovereignty. Nations that cannot power their own AI will be forced to export their data and import their intelligence. They risk becoming the digital colonies of the new energy empires. Faced with this looming crisis, the world is entering an energy arms race. The frantic search for gigawatts is leading to pragmatic and sometimes revolutionary solutions. This isn't just about more solar panels, it's a scramble for any source of reliable, scalable power. In the immediate term, we're seeing a dash for gas. Natural gas, while a fossil fuel, is dispatchable. A gas plant can be spun up quickly to meet the sudden, massive demand of a data center. For many utilities, it's the only viable short-term option. It's a messy compromise, pitting climate goals against the march of technology. But the most profound shift is the dramatic return of nuclear energy. For decades, nuclear power was politically toxic in much of the West. The AI energy crisis has changed the calculus. Nuclear offers something wind and solar cannot: a dense, carbon-free source of baseload power that runs 24/7, perfectly matching the relentless appetite of a data center. Big tech is taking notice. In a landmark move, Amazon signed a deal to acquire a data center campus in Pennsylvania, powered directly by an adjacent nuclear plant. More recently, they've expanded that into a long-term agreement to buy nearly 2 gigawatts of nuclear power from the same facility, a deal running until at least 2042. This isn't a small experiment. It's one of the world's largest companies making a multi-billion-dollar bet that nuclear power is the future of AI. This is just the beginning. Tech giants are now looking beyond traditional reactors and pouring money into the next generation of nuclear technology: small modular reactors, or SMRs. These are smaller, factory-built reactors that promise to be cheaper and faster to build. Some are even looking toward the holy grail, nuclear fusion. Microsoft signed the world's first power purchase agreement for fusion energy with the startup Helion. Helion aims to have its first fusion plant online, delivering power to Microsoft as early as 2028. The timeline is incredibly ambitious, but the very existence of this deal speaks volumes. The demand for power is so extreme that companies are willing to bet on recreating the power of the sun on Earth to meet it. The future of artificial intelligence may very well be powered by the atom. In this story of a technology threatening to overwhelm our energy systems, there is a final, crucial twist. AI is not just the cause of the crisis. It's also an indispensable part of the solution. We may need AI to solve the problems that AI creates. The same predictive capabilities that make AI so energy intensive can be turned back onto the grid itself. The power grid is one of the most complex machines ever built, and for a century we've operated it with relatively blunt instruments. AI offers a new level of precision. First, AI can radically improve grid management. By analyzing weather patterns and consumer behavior, AI can forecast renewable energy supply and electricity demand with stunning accuracy. This allows grid operators to better integrate intermittent sources like wind and solar, reducing the need to burn fossil fuels. Second, AI is the key to unlocking demand response on a massive scale. The idea is to intelligently shift energy consumption to align with supply. AI platforms can automatically coordinate millions of devices, from EV chargers and home batteries to industrial refrigerators. It can charge your car when electricity is cheapest, or subtly reduce a building's air conditioning to help avoid a blackout during a heat wave. This turns a grid of passive consumers into a smart, interactive network. Third, AI allows us to build a digital twin of the physical grid. By creating a hyper-realistic, real-time simulation of the entire energy network, operators can use AI to spot potential failures before they happen, optimize power flows, and war-game responses to disruptions like storms or cyber attacks. It's like giving the grid a nervous system and a brain. This friend and foe paradox is the tightrope we must walk. We are in a race to deploy AI to make our energy system smarter and more efficient, even as that same AI pushes the system to its absolute limit. Success depends on which side of the equation wins out, the drain or the optimization. Navigating this crisis requires a synchronized strategy. There is no single silver bullet. The future of a stable AI-powered world depends on advancing on 3 fronts simultaneously: hardware, policy, and philosophy. The first front is efficiency. The brute force approach of throwing ever more powerful GPUs at a problem is not sustainable. A green AI movement is emerging, focused on designing more efficient models. More importantly, the industry is racing to develop next-generation chips like neuromorphic processors, which mimic the human brain, or optical processors, which compute with light. These promise to perform AI calculations using a fraction of the energy of today's hardware. The second front is policy and investment. The market alone won't solve this. Governments must take a leading role in modernizing energy infrastructure. This means massive investment in the boring but essential work of building new, high-voltage transmission lines. It means streamlining the painfully slow permitting processes for clean energy projects, whether they are solar farms or next-generation nuclear reactors. And it means creating policies that reward companies and individuals for using power more intelligently. Finally, we need a philosophical shift. We must synchronize the development of AI with the development of our energy systems. For too long, the tech industry has operated as if the power would just be there, that innovation could happen in a vacuum and the physical world would simply adapt. That assumption is now broken. The mantra of move fast and break things takes on a terrifying new meaning when the thing being broken is the power grid that underpins our civilization. Future AI development cannot be divorced from its energy cost. The grid impact of a new model must be as important a metric as its performance. This requires a new era of collaboration between tech companies, utilities, and governments, all working to ensure the growth of one does not cause the collapse of the other. We began with a simple fact. An AI query uses about 10 times the power of a Google search. We've seen how that fact, scaled across the globe, is projected to cause data center energy demand to more than double by 2030, consuming an amount of power equivalent to an entire industrial nation like Japan. We've seen how this is pushing local power grids to the brink, driving up electricity bills, and creating a new geopolitical battlefield where cheap energy is the ultimate weapon. The AI revolution is here, but its promise is built on a foundation of electricity, and that foundation is beginning to crack. The race to lead the 21st century is no longer just about who has the fastest chips or the best code. It has become a far more primal contest, a race for power. This is one of the biggest stories of our time, a collision of technology, economics, and geopolitics that will shape the world you live in. What do you think? Which nations are best positioned to win this energy race? Are you already seeing the impacts on your own electricity bills? Let us know in the comments below. And if you want to stay ahead of how technology is radically reshaping our world, make sure you subscribe. The future is being built, 1 gigawatt at a time. You'll want to see what happens next.